We've now dealt with a variety of matrix operations, including matrix vector multiplication. And so as with working with real numbers, as we've been doing in algebra for many years, there are properties that happen to be useful. And although these properties may look very, very similar to properties that we've seen before, we have to be careful to assume that they are true. So let's start with just a couple of valuable properties. If A is an m by n matrix, so A has m rows and n columns, so this could be a 2 by 3, a 5 by 6, a 4 by 4, a 7 by 12, a 12 by 7, it doesn't really matter. The dimensions may or may not be the same for the rows and columns. And then U and V are vectors in Rn. Okay, so notice the correspondence here. The number of columns in A is the same as the number of rows in U and V. Okay, so if A is m by n, for example, if A would be a 2 by 3 matrix, then it would have 2 rows and 3 columns. And in that case, we know that in order for this product to take place, U and V would have to be 3 by 1. 3 by 1, based on the fact that we know that each one of these values in U is going to scale one of the 3 columns in A. Okay, so that's why these vectors have to be in Rn. And then let's suppose C is some scalar. Okay, so C is just a number. It's some constant. It could be negative, positive, 0, whatever. Then property A says that the matrix A multiplied by the sum of U and V. So the way this appears is that we would do what's in parentheses first. So we would add U and V together and then multiply by A. And this is suggesting that we get the same result as if we take A times U, we take A times V, and we then finally add these two results together. Right? So this gives us two ways of doing the same problem. We could add U and V first, and then multiply by A, or we could multiply U by A, multiply V by A, and then add the results together. So this is known as the distributive property. So why do we need to prove it? Because we know, after all, that if we take something like 3 times 2 plus 4, then one way we could do this is to add 2 and 4 together and we get 6. So this would be 3 times 6, which is 18. Or we could take 3 times 2 and add that to 3 times 4. So in this sense, we're doing 3 times 2 first, 3 times 4 second, and then adding the result. Here we would get 6 plus 12, which is also 18. And so we see that, all right, the distributive property holds here. But we have to be really careful here because we're not dealing with numbers. We're dealing with collections of numbers. And the way in which we multiply matrices and vectors are not, it's not straight across. It's this idea that each one of these elements in U scales one of the columns in A, and then we add all of those products together. So how do we go about proving something like this? Because it might be tempting to just assume that distributive property works regardless of what kind of data structure you're working with. But the subtlety again here is that we're working with matrices. We're not working with 3 individual distinct numbers. So let's just consider the intuition of, let's just consider A to be a 2 by 2 matrix. So this is just going to establish this for the 2 by 2 case. And let's just say that A has components A11, A12, A21, and A22. So sometimes we use lowercase letters to denote the elements of the matrix, the capital letter of the same name. So 1, means first row, first column, A12 means first row, second column, and similarly for A21 and A22. Now let's define U to be U1 and U2. So that we'll just say that those are the elements. And we'll define V to be the elements v1 and v2. So v1 and v2 are just numbers, u1 and u2 are just numbers. The key here is to take it from matrix vector form and represent it in a scalar form. So we know that these things can be carried out, these multiplications can be done. And so what we want to prove in part A is that whether we do what's on the left, add u and v together first and then multiply by a, or multiply a by u and then multiply a by v and add them together, that we get the exact same answer. That in other words, the left-hand side equals the right-hand side. So let's go with a times u plus v, which is our left-hand side. And if we do the instructions here in the correct order, by order of operations, parentheses still mean do parentheses first. Okay, so I'm going to write this all out. I'm going to write this as a times, and in the parentheses I'll just put in the two vectors that we're dealing with in their component form. Okay, I'm not writing a out yet just so I can save some space. Now that is equal to, well, I can add those vectors together, so I have a times, if I add these vectors together, I get u1 gets added to v1, the top components, u2 gets added to v2, and now I need to compute this product. So now I'm going to actually write out the components of a. So a11, a12, a21, a22. Okay, this is going to be multiplied by the vector consisting of u1 plus v1 and u2 plus v2. Now don't let your eyes deceive you here. u1 plus v1 is a single number. That's the sum of two numbers. So that's going to be a single number. And u2 plus v2 is also just a single number. And the way we multiply a matrix times a vector is that this scalar will multiply this column, this scalar will multiply this column, and then we'll add the results together. Okay, so now that we've added u and v, we're ready to conduct the multiplication. So what we'll have is u1 plus v1, that number, remember that's just a single number, that will multiply a11, a21, that vector. u2 plus v2, again just a single number, that will multiply a12, a22. Now one thing you can do here is you can call this, I don't know, something like z1 and z2, just for simplicity, just to be able to see that all we're doing here is taking a number times a11 and a number times a21. Okay, now if I distribute this through, z1 times a11 will be a11 times z1, and here we'll also multiply into a21. Over here we'll have the similar result, a12 times the number u2 plus v2. I'm just choosing to write u2 plus v2 on the right-hand side just because we know that when you multiply two numbers, the commutative property holds. 3 times 4 is 4 times 3. It doesn't matter what order you multiply two numbers in. Down here we'll have a22 times u2 plus v2. All right. Now here we can distribute because these are just numbers, and we know that the distributive property holds for real numbers. So I can multiply through a11 times u1 plus a11 times v1. And then I'm just going to go ahead and add all the components together because that's going to add to what we get when we distribute here, plus a12 u2 plus a12 v2. And down here, again, I'll distribute a21, a21 u1 plus a21 v1. Down here, I'll have a22 u2 plus a22 v2. Now, once again, keep in mind that this is a bunch of additions and multiplications. So this is a single number right here. That's just a single number. And this down here is a bunch of additions and multiplications. So that's just a single number. Okay, so if we had numerical values, we could condense this down into a single real value. And so there's our 2 by 1 vector that we would get. We took a 2 by 2 matrix, multiplied it by a 2 by 1 vector. This has 2 rows and it's 1 column. Don't let the pluses and multiplications make you think otherwise. That's a 2 by 1 vector right there. Now that's just my expansion of the left-hand side. Now we're going to see work on the right-hand side. Okay, so we're going to work on what we would get if we took A times U plus A times V. Now hopefully we're going to get the same answer as we get over here. Now how far you take it, I just kind of know that this is a way that we can get them to look exactly the same, but we really can't expand out more than what we have in our left-hand side expansion at this point right here. So let's expand out what we would get if we took AU plus AV. Now remember, this says take A, multiply it by U, take A, multiply it by V, and then add the results together. So if I took U1 times this first column, I would have U1 times A11, A21, plus, by the definition of matrix vector multiplication, I would have U2, A12, A22. And again, the key here is that we're working with scalars now. So now any scalar properties that we know of, and maybe you're not familiar with the word scalar, real number properties like distributive property we know are true, and so we can use anything that we already have come into this class knowing. Here I'll do the same thing, V1 times A11 A21 plus V2 times A12 A22. And so now as I add these together, I'm going to have U1 A11, or rather I'm going to keep things in the same order. I'll have the A's listed and then times U1, because again we're operating on real numbers now. Here I'll have A21 times U1. Now I'll be adding, right? I'll be adding all the way across. So here I'll have plus A12 U2 plus A11 V1, that's this times this, plus A12 V2. And you can see that, look at that, we're actually getting the same terms, right? Here's our A11 U1. Well, we'll come back and do that. Let's do this bottom row first. Here we have A22 U2 plus A21 V1 plus A22 V2. And now we just need to check that this red vector, this 2 by 1 red vector, is the same as this green one. So we just need to check up on all the terms. So here I have an A11 U1. Here I have an A11 U1. Here I have an A11 V1 in both results. I have an A12 U2, A12 U2, A12 V2, A12 V2. So the top row of the right-hand side expansion is the same as the top row of the left-hand side expansion. So far they're equal. Here I have an A21 U1. Here I have an A21 U1. Here I have an A22 U2. Here I have an A22 U2. A21 V1. A22 V2. And we see that we get the identical result. Now, why that is true is because notice that once we get to this stage right here, and once we get to this stage right here, we can almost see that we're going to end up getting the same thing. Because now U1 plus V1, U1 and V1 are both going to distribute with A11, A21. Namely, those two vectors are the same there. Here we'll have U2 plus V2 distribute into A12, A22. And now I can talk about the distributive property because, again, now I'm down at the fundamental real number level. Our property started off as symbols representing matrices, and we got it into a form where our symbols were expanded out into their real number formats. And again, once we're dealing with real numbers and not just matrices, then we can make arguments about the matrices based upon their real number properties. So that's the trick in proving things, is to get it into a form where we're operating with real numbers instead of with matrices. Now, I've only done this for a 2 by 2 case, right? We want to show that this is true for an m by n, but we could use similar reasoning. We would just have to do something a little bit more generic. So for the m by n case, we would have to write A something like this. We would have to say that this would be A11, A12, all the way out to A1n. It's the first row, nth column. And then A21, A22, all the way out to A2n. Eventually, we would get to the mth row, first column, mth row, second column, all the way out to the mth row, nth column. And you can see that we just can't fill in all the dots in there because we don't know how big m is. We don't know how big n is. This could be 100 by 500. And in that case, u would have to be written as an n by 1 vector. So u1, u2, all the way down to, it's going to have n components. V would be written out as an n by 1. Again, we have to do this dot, dot, dot to indicate that that vector can go on for a long time. And now we can almost kind of visualize how this is going to pan out. If we did a times u plus v, well, to add u and v together first, we would have to add u1 plus v1, u2 plus v2, all the way down to un plus vn. And that's the best we could do right there, right? Now, in our 2 by 2 case, where a was a 2 by 2, we only had 2 rows here. But now we can just imagine that this product involving a and u plus v is just not going to have these 2 scalar vector products, but it's going to have a whole bunch of them, right? Instead of this running out of room after u2 plus v2, this would kind of look like plus dot 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 plus un plus vn, because again we have n components and these vectors would continue on down as well. You can kind of imagine what that would look like. Just a lot more components. And we're just going to stop with the 2 by 2 case because it does kind of illustrate the logic of it, and that's really the key of this video, is just to illustrate how the logic would pan out. We would again have to take u plus v and write it in its generic form. We would get u1 plus v1 times a11, a21 down to am1, and we just have a whole bunch of these terms. And then to do the right-hand side expansion, we would again have to do something like involving u1 times the first column of a, a11, a21, all the way down to am1, and we'd have a bunch of these terms, and we'd have to logically show that they add together. Okay, so that's just kind of the outline that I'm trying to illustrate here. It just takes a lot of writing, but we can see the logic of it in the 2 by 2 case. Now in the second property, which I'll just briefly mention, a times cu is the same thing as c times au. Now what this suggests is that if you have a scalar multiplying a vector, you can actually factor that scalar out and multiply your end result by that scalar. So in other words, I can do a times u. I can factor out the scalar. I can't factor out a vector because that has to do with dimensional properties, but a scalar is just a single number, so it really doesn't matter where you multiply it. Okay, let me just do a brief illustration of this again. We'll use the same a, c, and u as in our 2 by 2 case for a. So if I take a times c times u, well, what would that look like? That's our left-hand side of the property. Well, that would be a11, a12, a21, a22 times some number times the u vector. And I encourage you to pause and try this on your own. We're just going to make the left-hand side look like the right-hand side. Okay, so based on what we do first, we do what's in parentheses, so this would just get copied down. I'm not going to write it again. C times u1, u2 would be cu1, cu2, based on how scalar multiplication of vectors is dealt with. And now we're actually going to take a11, a12, a21, a22, and multiply it by this vector, where cu1 and cu2 are just two real numbers. Okay, so we're going to get cu1 times a11, a21, plus cu2, a12, a22. Now, that maybe we'll want to take this a little bit further, but let me go ahead and operate on the right-hand side just to see if there's going to be a parallel somewhere where I could do a rearrangement. So let me see what the right-hand side would look like. The right-hand side would tell me multiply au first, or this is suggesting another way we could do it. So c times, well, we know au, what that will look like is it will be u1 times a11, a21, plus u2 times a21, a22, I'm sorry, a12, a22. And now we have a scalar distributing, right? This can distribute. We know that scalars can distribute. So this is the same thing as cu1, a11, a21, plus cu2 times a12, a22. And look at that. Those are the same. And that suggests that we could either first multiply u by that scalar and then multiply by a, or alternatively, we could choose to factor out the scalar, multiply, do the matrix vector multiplication, and then scale that result by the constant c. And either way gives us the same answer. The purpose of this video is just to show us that when we're thinking about properties of matrices and vectors, we have to be cautious because matrix vector arithmetic, especially with multiplication, is different than the way that we've encountered it in algebra. With that said, we'll go ahead and stop the video here.